Hi guys, you're welcome back to my channel. In this video, I'll be taking you through review exercises on functions. So we've delved into functions in our previous lessons. So we have some few problems here for us to solve. So it says, which of the following are not polynomial functions? Which of the following are not polynomial functions? So let's see how to handle this problem. So before you can solve this problem, you have to know what polynomial functions is, right? So the word polynomial, as you know, polynomial, right? Meaning that you are having, when you hear poly means, it means that a group of something, right? Or a complicated form of a particular unit, right? So we have what you call a monomial, So when you sum a series of monomial, or sorry, a sequence of monomial, you get a polynomial. Okay, so what do we mean by polynomial functions? Briefly, let me explain it to you. When you have ax to the power n, this is the general form of a monomial. Okay, so this is what we are supposed to classify as a polynomial, but based on certain conditions. So for you to get a polynomial, a that you see here should be non-zero. Okay, the a should be a number greater than 0. It can also be negative, just that it shouldn't be 0. Okay, it shouldn't be 0. Then the n here, which is the power, the n which is power can only be positive. Now it can also be 0. N can be 0, but can only be positive. You know, when n is 0, you are going to get a, which is a constant. And yes, a constant can be a polynomial function or a monomial. But n can't be a negative or a fraction. When n turns negative, it becomes a reciprocal function. When it turns fraction, it becomes a radical function. So now, as I said, n should not be negative nor fraction, but should only be positive. A should be non-zero. So now let's go straight to what we have here. So taking number 1, I have the a part to be f of x is equal to 1, right? So I have this f of x is equal to 1. Is this a polynomial function? Oh yes, from the explanation I gave here, I said that a should be non-zero, but n here can be 0. So this is an instance where we have our power n to go 0, having the x term out, right? So this is a perfect example of a polynomial function. But the question is saying that which of the following are not polynomial functions? So meaning we wouldn't include this as part of our solution. So we are just testing. Yes, so a is a polynomial function. That's what I've taken as the mark, right? Now let's go to b. The b is saying that I have b where this f of x is equal to x squared plus x to the power negative 1 plus 1, right? And what you're going to do is take each term. I said each term is a monomial. Together you get a polynomial, right? So the power of this x is 2, which is positive. Yes, and it satisfies. Now let's come here. X to the power negative 1. So the negative 1 here is making this function a reciprocal function. For that reason, this whole thing doesn't qualify to be a polynomial function. So as part of our answer, this is included as functions which are not polynomial. Now let's see the third one, which is f of x is equal to negative 2x cubed plus x to the power 1 out of 2 minus 1, right? So once you have this function, the same scenario. So the first one is a perfect monomial. A is negative and n is greater than 0, or greater than or equal to 0, but not negative. Then here the power of x is half, making it a radical function. So once we have a radical term, we can't classify this as a polynomial function. Finally, the d, which is f of x is equal to x to the power 4 square root of 5 minus pi. Now let's take notice of this. Don't be confused that this is a radical function. I gave a condition that n, which is the power of our x, is only the one to consider in terms of reciprocal, radical, and probably polynomial function. So when you have here, you realize that the n here is 4 and it's satisfied. This is the a part. A, the only condition is that it shouldn't be 0. Once a is not 0, whatever is attached to a, which is a non-zero number, is valid. Hence, this is a polynomial function. So to answer the whole question, you realize that our b and c are not polynomial functions. So this and this are not polynomial functions, right? Now let's go to the second section. Find the range of the following polynomial function. the range of the following polynomial function. What do you mean by the range of a function? So in our lessons on range, we spoke about it and we've solved several problems, right? So if you want to determine the range for a particular function, all that you need is the output of that function. What is the output of this function, right? What is the output of this function? Now, before you can get a range, always have your domain down. So let's take the first one, a. So a is f of x is equal to x squared plus 6, right? X squared plus 6. So once you have this, you know that the domain for this function is a set of all input numbers, a set of all inputs, right? So here the domain is all raw numbers r. But what will be the outcome? For you to get the outcome, you need the smallest number you can get as an output, and you need the biggest number you can get, so that we create an interval for that, right? So now let's see what will be the smallest number you ever get from this. Because this is squared, whenever a negative number is here, it will be squared, it will be positive. So the smallest input can be 0, right? The smallest valid input can be 0. And once you have 0, the smallest is 6. So meaning that in our interval for writing the range, we are going to have 6 as our small number, and it can go up to infinity, positive infinity, like this. So this becomes a perfect range for our function. Let's take the b. Negative 2x to the power 4 minus 6, which is equal to f of x. If you have this function, that is our b part here. If you have this function here, right, we have been asked to find the range of this function. How do we get the range? The domain of this function, normally the domain of all polynomial functions is a set of what? All raw numbers, right? Whenever you have a polynomial function, the domain is a set of all raw numbers. But we are looking out for the smallest and the biggest number that can come out of what? This, okay? So what will be the smallest number? The smallest number that can come out of this function, the smallest number. So to get the smallest number, we will look out for the least number we can put into this function. X is to the power 4. When I put a negative number, it becomes positive. So at all instants, everything we put here will yield a positive. But once you multiply it by the external negative 2, which is the coefficient here, we are going to get a negative output, right? But right now, we are looking out for the smallest number we will ever get. Meaning that you can't say that when I put 0 here, everything is 0. So the smallest number will be negative 6. No, I can't say that. This is because if I put, let's say, 2 here, I'll get 2 to the power 4 and I'm getting 16, right? The 16 will multiply by 2 here and I'll get negative 32. And after you subtract minus 6, making it negative 38, that means I can't choose 0 as the smallest number. Hence, for here, the smallest number can be infinity, and specifically negative infinity. So I'll have negative infinity as my smallest number. Can I ever get positive number here? Can I ever get positive number here? So I think for here, there is no means I can get a positive number. For that reason, we have to simply get a single range. So our range is simply defined as what? A set of what? Negative real numbers. That would be the perfect range. A set of what? All negative real numbers. A set of all negative real numbers. So for that reason, you can also make it like negative, I'm sorry, 0 probably to negative infinity to 0, because it will never reach positive. Okay, so it will never reach positive. So negative infinity comma 0 out, right? Now let's see here. C is saying that I have this f of x is equal to negative 2x cubed plus 1. F of x is equal to negative 2x cubed plus 1, right? So to find the range of this function, I'll ask myself, the x is to a power odd number. When I put negative number, I get negative outputs. But the negative 2 outside will turn it towards a positive number. Hence, the resultant will be what? Positive for all negative inputs, right? When x is 0, I'm going to get 1. So everything will be 0. So I'll be left with what? 1 as my smallest number. Now, what about when s is positive? When s is positive, I can get something like, when I put, let's say, 2 inside, I'll get 2 to the power 3, making it 8, right? So with this 8, I'll multiply negative 2 by 8. This negative 2 here, I'll multiply it by 8. When I multiply, I'll get negative 16. Then I'll add a 1. Then I'll get negative 15. But you realize that negative 15 is very, very small. Meaning that to get a minimum output of this function, 0 cannot be. 0 wouldn't be the input to give us the minimum. It will be the maximum positive number. Because when I put positive infinity here, I'll be getting negative infinity. So meaning that my least output I'll ever get is what? Negative infinity. Now what about the highest output? You realize that when I put in negative infinity here, I'll get negative 2 times negative infinity all cube, right? This will make my solution negative infinity. So negative 2 times negative infinity, and I'll get what? Positive infinity. Meaning that my largest output is what? Positive infinity. This is also the same as a set of all raw numbers. That's all. So this is our range, as simple as that. Let's look at D. So for D, let me clean some patch here. Okay, some patch here. Okay, so let's see. D. F of x is equal to absolute of negative 2x cubed plus 1. To find the range of this function, you realize that this function can never bring out a negative output because the absolute sign outside the function is going to produce positive values all the time. For that reason, I can move ahead and say that my output is a set of all positive real numbers. A set of all positive. The least I can get out is probably 0. I can't get negative. So a set of what? All positive real numbers, which mathematically I can write it as an interval at 0 to positive infinity. Okay, 0 to positive infinity. So this is my set of what? Interval for the range. Now let's see E. E is 3 minus 2, 3 minus 4x. 3 minus 4x. The domain is given as negative 2, 8, right? Then, for this one, I've been given the domain. Okay, I've been given the domain. So now let's see. The domain is saying that the smallest number you can ever get is negative 2, which you can put into this function. And the highest is 8. That's all. So when I come, I'll just put negative 2. So 3 minus 4 multiplying negative 2. What am I getting? I'll get 3 plus 8, giving me 11. When I put 8 inside, I'll get 3 minus 4 multiplying 8, and this is giving me what? 3 minus 32, which is equal to negative 29. So meaning that the smallest number I'll ever get is negative 29, and it's inclusive because we put 8 inside. This 8 that we put inside was included. Okay, so negative 29, comma, negative 2 was in part. So comma 11, right? Like this. That's all. Let's see finally F right here, F, which is open bracket 2x minus 1 whole squared plus 1. Domain is equal to open negative infinity, comma, negative 1, union 1, comma, positive infinity. Like that. Okay, so now at this place, let's see, I have my domain to be from negative infinity to negative 1 union this, right? Now what will be the output of this function? You realize that the smallest number here is negative infinity and the largest is positive infinity. Let's analyze and see the outcome of this. Okay, so for the outcome of this, you realize that our function is divided into two. I have one part to be, so let me kind of draw. I have 0 here, I have positive 1, I have negative 1. So one part of the function is starting from, it's open. The negative 1 is not included, so open to infinity. The other part is also standing here to infinity. So meaning in my input I don't have 0. Okay, take note, I don't have 0 in my input. Okay, so I can't test with 0. I can only test with values on this side and also values on this side, right? So meaning that I can only test with what? -1 and probably 1. Let's see. So right now, if I test with let's test with the infinity sense. So if I have negative infinity here, okay, I'm going to have 2 multiplying negative infinity minus 1 all squared. This gives me negative infinity minus 1 all squared. Like at the end, I'm getting what? Positive infinity plus 1. Everything is positive infinity, right? Now when I put positive infinity to, I'm going to get what? Positive infinity, right? So meaning that I've realized that the largest number I can get out is what? Positive infinity. Positive infinity. That will be the biggest number I can get from this function. Now let's see the smallest part of the function. Now let's try putting the endpoint 1 and -1. When I put 1 here, I'm getting 2 multiplying 1 minus 1 all squared. This is giving me 2 minus 1, which is 1, and it's 1 plus 1 outside here, giving me 2, right? Now let me put -2 and let's see. Sorry, -1. When I put -1, I'm getting 2 multiplying -1 minus 1 all squared plus 1. This is -2 minus 1 all squared plus 1. So this becomes -3 squared is 9 plus 1, 10. So meaning that -1 gave me 10, then 1 gave me 2. So I can start with 2 as my smaller output. Therefore, my range, I'll simply write my range to be equal to probably 2 to positive infinity. 2 to positive infinity. Or I can also divide my range into 2 because I was getting 2 parts. So I'll have, for the 2 was for the positive 1 aspect. So I'll have 2 to positive infinity as one part, and I also have maybe 10 to positive infinity. But I realized that these two ranges, they overlap because within this I can get this range. That's why you have to finalize on 2 comma positive infinity. And that's all for the range of the polynomial function aspect. Let's tackle the last aspect of this section, and that is finding the period of a periodic function, right? Now, first of all, what's a periodic function? What do you mean by a function is periodic? So a function which is a periodic function, it's cyclic in nature. Okay, we call it cyclic. It's cyclostationary. Okay, it's actually a stationary function, just that it goes and comes back to where it is. So the period of this function, I'll have 1. F of x is equal to sine 2x. So sine 2x is now a sinusoidal function. Okay, mathematically you see it as this, but graphically and in signals it's somehow like this. It moves and comes back to as it is. Okay, so now what is the period of this? To get a period of a sinusoidal function, the general formula is saying that c is equal to 2 pi over b. Okay, 2 pi over b, where b is the coefficient of the x you see here. Coefficient of the x. So using this formula, you can see that I have 2 pi over 2, and that is giving me pi for the first part. Then the second part is f of x is equal to this one. It's equal to cosine of the expression -2x plus pi on 3. Now I'm going to get c to be equal to 2 pi, and my b here is -2, right? When I divide, I'm going to get negative pi. Okay, remember this pi out of 3 here is the phase difference. It has nothing to do with the period. Okay, it's simply how this function is leading a reference function. Okay, that is the phase difference, but the periodicity is influenced by the coefficient of x here. Now let's see the final third one, x minus sine x. Okay, now this x part is a linear component. So in applied electricity, we call it the DC component, right? So it's not touched or it's not sinusoidal. Now you only focus on the sine x that you have here. Using the formula 2 pi on b. What's our b here is 1. Okay, so we simply get 2 pi over 1, giving us what? 2 pi. So this is the end of our section of our review exercise on functions, and this is part 1. We'll be having part 2 in the next section. Thank you for watching. Please don't forget to subscribe, like, and share.